Ever wonder how things just change? You know, how a log turns into ash, or how some gooey batter bakes into a fluffy cake? Well, it's not magic. It's actually a kind of secret language. And today, we're going to decode that hidden script that runs our entire world: chemical reactions. So let's start with this. Imagine you're holding a simple, shiny strip of metal, magnesium. You add a little bit of heat, and then whoosh, it erupts in this blindingly bright white light, and all that's left is a bit of white powder. I mean, what just happened there? How does a solid piece of metal basically vanish and turn into light and dust? Well, this is a secret message that explains the whole thing. I know, it might look like some kind of weird code right now, but it's the exact sentence that describes what happened to that magnesium. And in this explainer, we're going to figure out how to read it together. So, what is a chemical reaction really? At its heart, it's just a process of transformation. It's kind of like a recipe. You take your starting ingredients, we call those reactants, and they rearrange themselves to become something totally new, the products. And these products have completely different properties. A shiny metal becomes a white powder. That's a chemical reaction in action. Okay, so this brings us to the language of chemistry itself. If you want to understand the recipes, you first have to understand the language they're written in, right? So let's break down how to read one of these chemical equations. Every single chemical equation has two basic parts. On the left side, you've got your reactants. Just think of those as all the ingredients you're mixing together in a bowl. Then you've got the arrow, which basically means transforms into. And on the right side, those are your products, the final dish you've created. Ingredients on the left, creation on the right. It's really as simple as that. But how can you tell if a reaction is even happening in the first place? Well, you've got to look for the clues. Is something changing color all of a sudden? Are there little bubbles of gas starting to fizz up? Does the container it's in feel like it's getting hotter or colder? Or maybe a solid just appears out of nowhere from a clear liquid. These are all the telltale signs that atoms are busy rearranging themselves right in front of your eyes. All right, let's talk about the single most important rule in all of chemistry. Seriously, this is an unbreakable law of the universe, and it governs every single reaction there is, from a star exploding to a simple antacid tablet fizzing away in a glass of water.
And this is it, the golden rule, the law of conservation of mass. Put simply, it means you can't just make stuff out of thin air, and you can't make it disappear either. Every single atom you start with has to be accounted for at the end of the reaction. They can swap partners, they can rearrange, but they are all still there. It's like nature's ultimate recycling program. Nothing is ever truly lost.
Which, of course, brings up a really important question. If no atoms are ever lost or gained, then why do we have to balance equations? Well, balancing isn't about changing the reaction itself. It's about making sure our written recipe, our equation, is actually following that unbreakable rule. It's our way of double-checking our work and proving we've counted every single atom. Let's actually try it with the equation for rust. So, step 1, we just count up the atoms. On the left side, we've got 1 iron atom, but on the right, we've got 3. Uh-oh, the scales aren't balanced. So for step 2, we've got to fix that. We place a big number 3 in front of the iron on the left. Now the irons match up. Okay, but now look at the oxygen and hydrogen. We just do the same thing. We put a 4 here, and that means we need a 4 over here, until we get to our final check. Let's see, 3 iron, 8 hydrogen, and 4 oxygen atoms on both sides. Perfect. The equation is balanced, and the law is satisfied. You know, once you get the hang of the language, you start to see that chemistry has these common storylines, these plot lines that just show up over and over again. These are what we call the main types of chemical reactions. And here are the 5 big ones you'll see most often. You've got combination, where 2 things come together to make one. Decomposition is the exact opposite. One thing breaks apart into a bunch of smaller things. Then there's displacement, double displacement, and a really important one called a redox reaction. Each one tells a totally different story about how atoms like to interact. Let's take a closer look at a double displacement reaction, because it's a fun one. The absolute best way to think about this is like 2 couples on a dance floor. So you've got sodium dancing with sulfate, and barium is dancing with chloride. They bump into each other on the floor, and they just swap partners. Now barium is with sulfate, and sodium is with chloride. It's a simple, elegant little exchange. And then you have redox. Now, this one sounds a little complicated, but the core idea is simple. One thing loses something, while another thing gains it. And a lot of the time, that something is oxygen. So the substance that gains the oxygen is oxidized. The one that loses the oxygen is reduced. The key is they always happen together.
Look at this example. The hydrogen grabs the oxygen from the copper oxide to become water, so the hydrogen gets oxidized. And at the exact same time, the copper oxide loses its oxygen and becomes pure copper. It gets reduced. See? One gains, one loses. Now, besides just changing substances from one thing to another, chemical reactions are also all about energy. They either release energy out into the world or they suck it up from their surroundings, and you can usually feel the difference. This gives us two more categories. An exothermic reaction is one where heat exits, making everything around it feel hotter. The easiest example is a campfire. That's a big exothermic reaction, releasing tons of heat and light. The opposite is an endothermic reaction, where heat has to enter the reaction, pulling it from its surroundings and making things feel cold. You know those instant cold packs you shake up? That's an endothermic reaction happening inside. And here's the most important takeaway. This is not just stuff that happens in a lab. These reactions, especially oxidation, are happening all around you, every single day, changing the very world you live in. I mean, have you ever seen an old bike or a car with those ugly, flaky, reddish-brown patches on it? That's rust. And rust is nothing more than a slow oxidation reaction. We call it corrosion. It's just iron reacting with the oxygen and water that's in the air. It's a chemical reaction playing out in slow motion. And believe it or not, the same exact process happens to your food. You know that kind of stale, nasty smell from an old bag of potato chips or some nuts that have been sitting around too long? That's called rancidity, and it's just the fats and oils in the food oxidizing when they get exposed to the air. It's the same basic chemistry as rust, just happening to your snack. But here's the good news. Once you understand the chemistry, you can actually fight back. To stop rust, you can paint or grease the metal, which creates a barrier to keep the oxygen out. And to keep your food from going rancid, you put it in an airtight container or stick it in the fridge to slow that reaction way down. See? It's all just practical chemistry. So, as we finish up here, I want to leave you with this thought. Now that you can spot the signs and you understand a little bit of the language, just look around. From the food you're about to eat to the air that you're breathing, chemistry is constantly writing and rewriting the story of our world. So what invisible reaction is changing your world right now?